here's the deal. First two slides here are basically reviews of basic chemistry from AP1 or from wherever. But just a couple things you need to remember. Water self-ionizes. In other words, water molecules spontaneously break down into hydrogen ions, often called protons, and hydroxide ions, right? And then it turns out that this is a reversible reaction. So any two of these that are formed will sometimes just come back together and make these. The end result is that natural water is a combination of molecular water, protons, and hydroxide ions. In other words, any water you're going to encounter, including the water in you, or any water you drink, this is what you're actually looking at. It will be a combination of these three things. Got me? All right, and you need to learn those terms because they're used quite a bit. So hydrogen ion, also called a proton, and hydroxide ion. All right. Now, that becomes important when we start talking about things like acidity and basicity or alkalinity, okay? So acids and bases. So the next slide is just to remind you how the pH scale works. pH scales measure the concentration of the protons, or H pluses, and the OH minuses in a water solution. Note, if it's water, it is going to have both of those things in it. That's unavoidable. So what you're doing with the pH when you're measuring the watery solution is you're talking about how much of each one is present. So if your pH scale is below 7, that means you've got a higher concentration of the H pluses than the OH minuses. All right, that's what a below 7 reading would mean. We would call that acidic because you got more of these. 7 is a neutral solution where the concentrations are equal between protons and hydroxide ions. Okay. If the pH scale is reading above 7, that means you have more of these, the hydroxides, than you do the hydrogens. So we call that an alkaline or basic solution. So when you hear the terms acids and bases involving water, this is what it's talking about. Okay? Now, why do we have to care? Well, it turns out it's super important. If you have too high a concentration of either one, it's going to cause you issues. And we're going to talk a little bit about the issues and summarize how you control all this in about 4 weeks. Okay? Give or take, maybe 5. Right, we're not going to get there yet. First, we have to figure out what's going on with breathing. Okay? But you need to understand the pH scale. pH scale runs from 0 to 14. So it can go as low as 0, as high as 14. But you need to understand how to read it based on this. Be very careful, because the pH scale is generally defined as measuring proton concentration, or H plus concentration, but it is what mathematicians call an inverse logarithmic scale. So the lower the number on the scale, the higher the proton concentration. That's why it reads like this. Below 7 means acidic or more of these. Above 7 actually means fewer of those. Okay? So, if I take an acid and I pour it into water, just pure water, and I pour this acid into the water, what's it going to do to the pH? It's going to lower it. Make it acidic. Students will miss questions. It doesn't matter what science class. In any science, if it involves pH, students will often get this messed up and miss the questions, okay? So remember, acidic is low pH, not high pH. All right. These are two equations you have to know and understand. Remember, we mentioned that you make ATP. Most of the ATP you make is made using this equation. You're going to take a food item, basic one is glucose. You can use other ones, which we'll talk about later, but they all work about the same way. You put the glucose, you use oxygen, and you can make ATP, and you get two waste products or byproducts. You get CO2 and H2O. Okay? I can't stress to you how important it is for you to remember that a cell is a living machine. We call it that. I don't know if there's some living and non-living, but it's a machine. It's using energy to do work. That work is staying alive. Okay? So, if you don't have energy, you're dead. Right? So, all cells in your body, all the trillions of cells, are always doing this. Because as soon as they quit, they'll soon run out of that and they're dead. Okay? So if they're always making the ATP, what are they also making? CO2 and water. Okay? Now, most of you probably are a little young, you hadn't thought about this. But as far as final dispensation of your body, when you no longer have need of it, it's older people, we think about those kinds of things. Whether you get cremated or you do whatever else you do, a lot of people end up with some kind of like memorial, like a headstone, a little box to keep your ashes, whatever. Two common things that are used for this are granite, the stone granite, right? Or marble. And I don't know how many of you hang out in graveyards. You ever go out to graveyards and jog or check it out or tourist or whatever? You know? I love graveyards. Nobody bothers me there. It's just nice. They're wonderful to jog in. I just have this one near the house. I love going jogging. All right, in the cemetery. But if you go, we don't have it in Florida much. But it's great if you go to one of the old ones, a couple 100 years old or whatever. You can read the tombstones, and they're really interesting. Like this so-and-so person died in the Revolutionary War, or whatever, killed by bubonic plague, whatever. Go to Europe, that's really cool. Well, the question though is which one do you want? Do you want granite or do you want marble? Okay. If you go to the cemeteries, they're both cool. They will have granite ones and they'll have marble ones. But if you start reading the tombstones in an older one, you'll find a very definite pattern. You can go up to ones made of granite, or sometimes sandstone, they use that. And they can be hundreds of years old, and you can still read everything on them. But a lot of times, the marble ones, there's nothing on them anymore. They're smooth. And the reason why is that marble dissolves fairly readily in acid. Granite is not. Okay. So why do you think the marble ones would be dissolving out in a cemetery? Could be pollution, it helps, but there's actually even more basic reason without the pollution. Well, it deals with this equation. You see, carbon dioxide and water, when you put them together, some of those molecules will combine to turn into this thing called carbonic acid. And then carbonic acid, some of those molecules, not all of them, but a few of them, will split apart into this. So this is an acid, and it releases these, which start interacting with the marble. Now the reason it happens, pollution can make it worse, but here's the thing. What's rain made of?
Water.
When it rains, the rain falls to the atmosphere, doesn't it? Yeah. And what's one of the gases in our atmosphere?
CO2.
Yes. So all rain is acidic in almost every case. Have you heard of acid rain? Acid rain is especially acidic, more than normal rain. All right. So in areas, they literally have a problem with this in a lot of Europe and other areas where they have really important old buildings and marble or something. They're literally having a lot of problem with them dissolving away because of modern air pollution. It accelerates it drastically. But even without the air pollution, there's normally a little acidity to rainwater, and it will dissolve. Now, you're gonna go write a bad review about me and talk about tombstones. I'm not gonna test you on tombstones, but I wanna get the point across to you. That whenever you have these two together, this chemical reaction occurs. Okay? There are different conditions that make it occur more or less, you know, chemistry, but it always occurs. And it's reversible. This one is not reversible. Once you make your ATP, you cannot make glucose and O2 out of it again. This one, however, is reversible. Because anytime you have some of these, a few of them will get together to make these. And some of those you made will actually split apart into these. It's a free-for-all. It just goes back and forth. The question is, on a given set of conditions, how much of each one of the components is there? And that varies based on various conditions, which we're not going to get all into. But in your mind, you need to get the concept. You basically cannot have one of these. You have to have all three present. You can't just take, I'm going to take some CO2 and water, and I'm going to put them together, and they're just going to stay CO2 in it. No. Some of them are going to become that, and some of them are going to become this. You can't take these and put them together and just stay like that. A few of them are going to become that, and some of them will become this. You see? All right. It's driven by concentrations. Remember, a chemical equation is a balance. It's just like an algebra equation. Remember the equal sign? What's on this side, by definition, equals what's on that one, correct? The arrows here are equal signs. They don't have equal signs in chemical equations, they have arrows. It's saying these equal that, equal that. Okay, that's what it's saying. So they're going to balance out. In the algebra equation, if you add 5 to one side, what do you have to do to the other side? Add 5 to keep it balanced. Here, you can add to one spot, but it's going to balance itself out. So in other words, if I have a mixture of these things, and I suddenly, they're all in a beaker, they're sitting right, and I dump a bunch of this into it, what would happen? Well, some of the molecules of this would stay just like this, but some of them would turn into these, and some of them would turn into these until they all balanced back to their original proportions. You see what I mean? That's how it happens. So if I wanted to somehow have all of this, and I go, wow, you know, I want more of these. I want more of those. But I don't have any. I don't have a bottle of those. How could I make more? According to the equation. I need more protons, more H pluses, but I don't have any. I'm going to die if I don't get them. You could. I'll explain that later. So what if you needed more H pluses? But how can I get more? According to the equation. Remember, everything's in flux. Everything there can convert to everything else, right? So how can I get more H pluses if I don't actually have any? You're about to die. Your patient's dying. You gotta help them. Okay, wait a minute. I like you said that. That's wrong, but I like you said that. Here's why. No, because you're thinking about converting. Remember, we can't turn this to that. These came from what? This. You got me? So this is a separate thing from that. So according to this equation, what could I do to get more H pluses?
Could you get more water?
All right. So are you saying add more water to it?
Yeah.
All right. We're kinda getting there, but in order for the water to become this, what do we need?
CO2.
Alright, so tell me what I can do to get more H pluses. I can dump more CO2 and water into it, correct?
Yeah.
Look, more CO2 and water would then turn into what?
Yeah.
And what's some of that gonna turn into?
H
There you go. You see what I mean?
Yeah.
It's not that hard, right? Once you get the concept. But I can't just add like CO2, I can also add carbonic acid. If I dump carbonic acid in it, what's the fate of the carbonic acid again? The extra carbonic acid I put in, right?
Yeah.
Some will stay carbonic acid, some would bounce over here, become this, and some would have to come over here. You with me? That's how it works. And you're gonna need to understand this because we're gonna talk a lot about what's going on with it a little today, but later in about 5 weeks, we're gonna talk about how your whole body regulates all this. All right. If you decide to get a chemical equation to do on this is the one you need to get. This is the most important. All right. Now, we're gonna finish up today with gas transport. All right. Now, this is part of the lecture. There's been other parts we covered too. But this is part very commonly. You need to pay close attention and focus on this. And you're probably going to have to go home and consider it and come back to questions next time. Okay? We're going to talk about 2 gases today, oxygen and carbon dioxide. Remember, you breathe in the air in the lungs. What good does that do to the big toe? Doesn't do it any good unless you get it to the big toe, right? Okay, and we went through that whole slide. It's got to do this and this and that, all right? Well, one of the things we said is, no matter what you got going on elsewhere, if you can get it into the blood in the lungs, if you're breathing in oxygen, for instance, right, the blood is what's going to take it to the big toe. Yes? So, how are we going to do that? Well, it turns out it's not as easy as you might think. Oxygen does not like dissolving in water, strangely enough. So your plasma is mostly water, that's where you would want to dissolve it, but you can only get about 1.5% of what your body needs to transport to dissolve in the water and the plasma. So almost all, 98.5%-ish, of the oxygen your body needs to transport from one place to another has to be bound to the protein hemoglobin in the red blood cells. That's why they're so important. Okay? So almost all of it has to be bound to the iron molecule in the hemoglobin. All right. Now, it's interesting to note and important for you to know, at rest about 25% of the O2 absorbed by the blood in the lungs is used after a single pass through the systemic circuit. This is what we mean by this. If we put a sensor for oxygen, an oxygen sensor in your left atrium, all right, and one in your right atrium, the blood in the left atrium is coming from where? All right, it's the best it gets, right? It's coming straight, hadn't been anywhere else, hadn't been used by anything. That's your highest oxygen content blood, correct? What about the blood in the right atrium? It's used up, it's been everywhere, right? It's gonna be your lowest. Well, if we compare the two, strangely enough, when you're not exercising, it's not as much difference as you might think. It's only a 25% difference. You still have about 75% of the absorbed oxygen in the right atrium. You got it? Okay. Who knows CPR? Who got trained in CPR? All right, good thing to know. Many years ago, I was a CPR instructor. Right. So how does this sound to you? You still remember your stuff? You still remember your compressions on that? All right, so this is what you're supposed to do, right? You do 1 breath, 5 compressions, 1 breath. Does that sound right? It was when I trained. Not anymore, right? Still 2 and 30, I think. Okay. Well, why'd they change it? There's a couple of things. But one of the reasons is they really fully understand that even after it's been through a whole circuit in your body, there's still more than enough oxygen in there to keep your tissues alive. If you're not doing, the main thing they want you to do is keep the blood circulating. Don't worry as much about the breathing, keep it circulating. All right? The other thing is you want to make it keep circulating and keep the pressure up, keep perfusion in the tissues and keep what oxygen in there going to the tissues. That's why they want all the compressions now. But in my day, no, they didn't do that. You see such a change. Just bear in mind, now when you exercise, this changes drastically. You can use a lot more than 25% if you're exercising. All right. Well, here's the deal. It makes me almost cry. All right, so I guess they still have ice cream trucks, don't they? Remember being a kid with were you lucky enough to have ice cream trucks that would come by and you're a kid? Oh my God, there's nothing better, man. And so you know how it was, like maybe they'd only come on one day a week or something like that, but you knew. And your parents would give you, I could get a quarter for like 2 things back in those days. But you're the kid, right? And you need the ice cream. Yeah. Well, how are you going to get the ice cream? The ice cream truck comes by. You get me the ice cream, you know. All right. And the truck stops, and you get your ice cream. Yeah. So how does it feel when you got the mean ice cream driver, and they see you, and they just keep going by? that's really mean, right? All right. Well, you see, on that particular day, the ice cream driver really didn't want to give you the ice cream. He just wasn't into it, right? Now, we can kind of change it around a little bit and say it like this. What if the ice cream driver is an ice creamaholic? They eat like 2 or 3 gallons a day or something, whatever. All right. Well, that ice cream you wanted, whether you get that ice cream or not might depend on how much the ice cream driver wants the ice cream. Are you with me? If they really want the ice cream themselves, you may not get it even if you got the dollar bill out there waiting. You see what I'm saying? So they have an affinity for ice cream. They love ice cream. Well, hemoglobin has an affinity for oxygen. How strong that affinity is determines whether or not the oxygen will bond to the hemoglobin or not. Another way of looking at it is if the ice cream driver that day has a strong affinity for the ice cream, you ain't getting any. If they have a low affinity, they don't care much about it, you'll get your ice cream. You with me? Okay. It's really important because, no, you're not a little kid with the ice cream in the body, but your cells need oxygen, yes? Who carries the oxygen? Hemoglobin. Right? Yeah, hemoglobin. So is the hemoglobin, when it comes to you, does it have a high affinity for the oxygen and therefore doesn't want to give it to you? Or does it have a low affinity and not really care about the oxygen, so it'll give it away to you? You with me? That's the key. These are the factors that affect the affinity between hemoglobin and oxygen. All right. I listed them as increasing affinity. If you reverse any of them, it decreases the affinity. All right. Now, so increase O2 pressure, decrease CO2, decrease. So I intentionally listed them so the first one is increase, and the next 3 are decrease. What you got to be careful of on the test is don't get them confused with whether you're increasing or decreasing affinity. Okay? So you're just going to practice. But let's see if this makes sense. You see, here's another concept I want you to get. If you're a cell where gas exchange is concerned, you've got 2 places to live. There's 2 real estate markets. There's in the lungs next to the alveoli, or being the alveoli themselves, or the capillaries right there on the alveoli. That's it's wonderful. I mean, it's paradise, right? And then there's everybody else. Because if you're in the lungs, oxygen is right there. It's right there. It rains oxygen. It's ice cream raining all over you, okay? It's there. You don't have to do anything for it. It's right there. You just like take a cone, stick it out, it falls in and you eat it. Okay, it's everywhere. But if you're anywhere else, you're stuck there, remember? If you're a cell, you don't move unless you're a blood cell, and you just get pumped wherever you're sent. But if you're in the big toe, you're the cell in the big toe, how are you going to get your oxygen? How are you going to get the ice cream? How do you get it? You're not in the lungs. So how does the oxygen get to you? Blood. Hemoglobin has to bring it to you. The ice cream truck has to come to you. All right. So there you are, waiting. Here comes the oxygen. Well, you're like, oxygen. Is the hemoglobin going to let go of the oxygen or not? That's the key. It may just go on by. All right? Or it might let it go. What's going to determine whether or not it lets it go? The affinity. All right, so let's think about this. You live in the big toe. You're not up in the, unfortunately, you're not in the big toe. You're in the big toe. What's life like? What do you do if you live in the big toe?
Get smushed over.
Yeah, I can tell you get smushed, you do whatever. But you and all your friends are doing what all cells do wherever they are. So if you're alive, you're doing what? All cells are doing what? You're making ATP, or you couldn't be alive, correct? All right, so if you're making ATP, what else are you making?
Carbon dioxide.
Carbon dioxide with the water, and when you do that, they combine to make carbonic acid, and they'll make things acidic. So realize, just by your mere existence in the big toe, or anywhere else, even in lungs, you are making CO2, you are using oxygen up. Okay, you're using oxygen to make CO2. The CO2 you're making is making the environment acidic. You got me? Yeah. So, if we went up to the lungs, however, plenty of oxygen. No matter how much you use, you couldn't use enough. It's oxygen everywhere. High oxygen. You're making CO2, but as soon as you make it, as it builds up, it diffuses out into the alveoli and gets exhaled. So it doesn't hang around. It's like having a garbage truck come to your house every day. All right, it takes everything away. So you're going to have high oxygen, low CO2. Well, if you have low CO2, you don't have anything to make the environment acidic, do you? Because isn't that where the acidity is coming from? Yeah. So that's your situation. So you see, where you live as the cell is going to determine these things, 3 of them at least. So let's say you are down in the big toe. You're going to have low oxygen there relatively. All right? So it says increase. Well, you're not going to be increasing, you're going to be decreasing. You have low O2 pressure, so that would decrease the affinity between the oxygen and hemoglobin, right? Well, that's good, because you need that oxygen. So since you have low oxygen in the area, the ice cream man gives you the ice cream. You get the oxygen, because there's low affinity. Same with CO2. There'd be high CO2 relatively around you, because you're making it a lot. And nothing is taking it away except the blood. So once again, it tends to give up the oxygen. Same thing with acidity. You have low affinity because of the acidity, and therefore it tends to release it. Up in the lungs, we have the opposite. These would apply. We have high O2 pressure, decreased CO2, decreased acidity in the lungs, and that's good because you want the hemoglobin to snatch all the oxygen it can and hold on to it, because the cells there don't need you. They don't need the hemoglobin. They got their own oxygen. That's how it's working. So think about it like that. As far as temperature concerns, is concerned. Makes sense. When you start exercising, all that muscular activity generates a lot of heat, doesn't it? So you start doing that, you want to make sure that if you've got increasing temperature, not decreasing, you want a low affinity to release the oxygen to your muscles. Okay? So walk these through in your mind and see that they make sense. Now on a test, it's going to be very straightforward. I'm not going to ask you any big discussion questions. I'm going to just simply say, which one of these increases or decreases affinity? And then I might ask you, all right, if you were in the systemic capillaries as opposed to the pulmonary, which one of these do you expect to see? You'd like to see a higher CO2 or lower CO2 constant, something like that, okay? Now, we're going to do our gases real quick here. So we're going to actually look, we're going to look at CO2 next as our gas. The carbon dioxide, you can dissolve more of it in the water and the plasma than you can oxygen, but still only about 7% of what you need, okay? You can actually bound some to hemoglobin as well. You can bind it to it, so that's still only about 23% though what you need to be able to transport. The majority of what you need to transport in the blood, what you're going to have to do is convert the CO2 to bicarbonate. And bicarbonate dissolves really well in water. Okay? So about 70% of what you're going to carry in the blood is going to be as bicarbonate. And so that's another way this reaction becomes very important. In order to get that CO2 out of the pinky toe, sorry, out of the big toe, that's what I was talking about. If you need to get your CO2 away from you, you don't have a lung in you, get rid of it. So the only person that's going to take it from you is the hemoglobin. So the hemoglobin picks up the CO2, some of it, but that's all it can hold. What else are you going to do? Well, it turns out there's an enzyme called carbonic anhydrase inside the red blood cell. And what that does is accelerate this reaction so that CO2 getting into the red blood cell will be converted into carbonic acid and then quickly converted into these. These will then leave the red blood cell and can easily dissolve in the water and plasma. That's what's happening. That is all summarized along with your oxygen transport in these figures. And so what I want you to do is look at the previous 4 slides and then look at these and see if these chemical equations make sense. What they've done is this is what is happening in the pulmonary capillaries. This is the systemic. All right. So they're showing you the actual chemical reactions and things that can happen. You'll notice fairly quickly, one is just a reverse of the other one. All these are reverses of this. So to give you an example and walk you through, let's look at CO2 in the systemic. All right. You're down here in the big toe. You're making CO2. It'll build up and kill you if you don't get rid of it. As it builds up, it'll diffuse away. We know how that diffusion thing works. It'll diffuse from where there's more of it to less of it. So it'll diffuse into the bloodstream. Some of that CO2 will dissolve immediately into the water, into the plasma, and stay CO2. All right? It's only 7%. The rest, 93%, has to enter the red blood cell. Some of that will bind the hemoglobin. So now the hemoglobin will keep it in the red blood cell to take it away. You got me? All right. However, most of it, you're going to have to convert it through the chemical reaction, the carbonic acid equation, and make it into bicarbonate. Once you've made it into bicarbonate, it gets transferred outside the cell. And now this will dissolve out here in the plasma along with some of the CO2. And now you can just carry it through the blood, through the plasma, up to the lungs. When you get to the lungs, you'll notice the whole thing is reversed so that your bicarbonate gets drawn in, converted to CO2, and then the CO2 diffuses into the blood, and then it can diffuse into your alveoli and be exhaled. And get rid of it. See little people squinting. I want you to look this over and look at the other slide and see if you can make it make sense, okay?
What kind of question would you ask on the test?
What kind of question? Oh heavens. So I could ask you, okay, if you're in the systemic, which way would the carbonic acid equation be going, from left to right? Which one would we be converting? So would you be converting CO2 into bicarbonate in the systemic, or would you be doing that up in the pulmonary? Right? So it all revolves around this equation. All right, as far as CO2 bicarbonate goes. Note, and this is where you don't get it messed up, students will often get freaked out because they're missing the big picture looking at the little equation. Where is the CO2 in this equation coming from?
Aerobic respiration.
Aerobic respiration, which is happening where?
In the cells.
All your cells. You see, people get hung up on this. There's CO2 in the atmosphere, right? The air you're breathing. Why is there CO2 in the atmosphere, the air you're breathing?
Because you're exhaling out.
There's a whole bunch of things on the planet going, breathing it all out everywhere, right? That's the reason why it's there mostly. It also comes from volcanoes, but that's one of the reasons. So students will get freaked out and think that somehow you're getting the CO2 from your lungs. No. You're making way more CO2 in your body than is ever out here in the atmosphere, which is good because it kills us. And you depend on that for it to diffuse out into the air and you exhale it, right? So the lung activity gets rid of CO2. That's what's happening. All right, that's it for today. That's enough brain damage. We will pick up with this and we'll do digestive. We can get through this and digestive in one day. If you get through this and you want to start with digestive, go ahead and start learning your parts. And you might even start looking at the slideshow because it's fairly straightforward. I don't run any test dates. Nope. What we have to do is combine lectures.
What?
Yeah.
Because
Yeah.
I know for it,
I'm honestly freaking out about that.